The last example problem in this chapter is all about Reynolds number. So Reynolds number is concerned with whether flow is laminar, which means that it's straight and there's no disturbance in it, or whether flow is turbulent. So it would be going in all different directions, very disruptive kind of flow. You guys have probably experienced turbulence before if you've ridden on an airplane. So when the captain comes over the overhead and says, put your seatbelt on because we're going into some turbulence, it gets really bumpy. You can get really nauseated sometimes because the disturbance can be so significant. And so that's what turbulence is. It's disturbed flow. The variable for Reynolds number is RE. And that is what we're ultimately going to be looking for in example problem 2. And so if RE is greater than 3,000, then that means that the flow is turbulent. If it's less than 2,000, then it means that the flow is laminar. And so example problem 2 reads, a drug is being delivered into a patient's arm at a rate of 319.0 milliliters per minute. So right off the bat, we have a volume flow rate of 319 milliliters per 1 minute. And we're going to go ahead and handle that and put that into the correct units, which is cubic meters per second. So we're going to do this pretty quickly because we've done this several times at this point. And then handling minutes and seconds. And so give the 1 to the thing with the prefix. Metric system constant to the base unit. In 1 liter, there is 0.001 cubic meter, and that is right here. And in 1 minute, there are 60 seconds. And so milliliters cancels, liters cancels, you're left in cubic meters. Minutes cancels, and you're left in seconds. So in your calculators, 319 times 1 times 10 to the minus 3 times 0.001 divided by 60 equals 5.32 or 5.316. So 5.32 times 10 to the minus 6 cubic meters per second. So continuing on with the problem, this drug is being delivered from a syringe through a needle with an internal diameter of 1.0 millimeters. And so this is what's going to correspond to the L. And so L equals 1.0 millimeter, but we know that that's not the correct units. It needs to be in units of meters. So we're going to go ahead and draw our multiplication symbol, draw the division bar. Millimeters goes to the bottom and meters goes to the top, giving the 1 to the thing with the prefix and the metric system constant to the base unit. Millimeters cancels and you're left in meters. And so we know that 1 times anything is going to be itself, right? So it's going to be 1 times 10 to the minus 3 or 0.001 meters. And so that's what's going to be our L. This drug has a density of 1050 kilograms. So density of 1050 kilograms meters minus 3. And yes, that is the correct unit. For density in this problem, it does not need to be converted into grams over milliliters. And so it's asking us for Reynolds number. So is it laminar or is it turbulent? And then it gives us a viscosity of 8.90 times 10 to the minus 4th pascals per second. And so if you switch over to the previous slide, you'll see that the formula for Reynolds number equals density times velocity times length divided by viscosity. And so nowhere in here did I see anything about a velocity. So we know we're going to be using this volume flow rate over here to calculate that velocity. So the volume flow rate equation is area times velocity. We're looking for this velocity. So we're going to divide by area to make it cancel. Our rearranged equation is going to be velocity equals volume flow rate divided by area. So we know our volume flow rate already, which is 5.32 times 10 to the minus 6 meters 3 per second divided by the area, which we don't know. But we're given some formulas here to try and calculate area. So we know that area equals pi r squared. And we're given a diameter of 1 millimeter. And so we're told that the radius to be able to use this equation over here is the diameter divided by 2. So we should take 1 millimeter divided by 2. So 1 divided by 2 is going to be 0.5. And this is millimeters. And this is now a radius. This is no longer a diameter. Once you divide it by 2, it becomes a radius. But we can't use millimeters. We have to use meters, because that's how these equations work. So giving the 1 to the thing with the prefix, the metric system constant to the base unit, milli cancels and we're left in meters. So 0.5 divided by, or 0.5 times 1 times 10 to the minus third, and that equals 5.0 times 10 to the minus 4 meters. And I'm just going to rewrite this because I can barely see. So 5.0 times 10 to the minus 4 meters. That looks much better. And so now we have our radius in units of meters, and we're ready to plug that information into the area equation to get the area. So area equals pi, which is 3.14, times the radius squared, which is 5.0, times 10 to the minus 4 squared. And so in your calculators, do the squared first. So 5.0, second e to the minus 4 squared, times 3.14 equals 7.85. So 7.85 times 10 to the minus 7 meters squared. And we're going to go ahead and plug that area in up here because that's what we did to get that. So 7.85 times 10 to the minus 7 meters squared. So in your calculator, 5.32 second e to the minus 6 divided by 7.85 second e to the minus 7 equals a velocity, and I'm kind of running out of space to put it, so I'll go ahead and write it down here. Velocity equals 6.777 or 6.78 meters per second. So now we have an L, we have a V, we have a density that's given to us in the problem, and we have a viscosity. And so now we're finally ready to put everything into the Reynolds number equation. So the density from over here, 1050 kilograms meters minus 3. The velocity that we calculated was 6.78 meters per second. The length in units of meters over here that we calculated is 0.001 meters, all divided by the viscosity that we were given for the drug, so 8.90 times 10 to the minus 4 pascals per second. And so for the numerator, 1050, 6.78, 0.001, divide that by 8.90, second e to the minus 4, and that equals a Reynolds number of 7,998.876, so 0.88. There's no units attached to this. Everything cancels. And so this is your Reynolds number. So it's asking you, is the flow laminar or turbulent? And so 7,000 to basically 8,000, 7,998, 8,000 is way greater than 3,000. So this is going to be turbulent flow, not laminar flow. It's going to be turbulent flow. Let me know if you have any questions about example problem